Hello. Today I will guide you through on making a simple IoT device from scratch using our W5100S-EVB-Pico 2 and operate with CircuitPython and Adafruit's IoT interface. This basic program using the W5100S-EVB-Pico 2 can turn on or off the lights from red to green by moving our joystick or pressing the controller on Adafruit IO. We can also toggle the power of the device on the platform. In this video, we will explain each step of this project, starting from hardware configuration, then to software implementation, and lastly the Python codes needed for our project. By following this video, you could learn how to set up our board and how to connect our board to the internet using CircuitPython to create your own IoT project. Let's start by preparing the hardware components. For this project, you need to prepare these hardware components, which are an Ethernet cable, some electronic wires, a USB to Type-C cable, a rocker module, a traffic light module, and lastly our W5100S-EVB-Pico 2. The W5100S-EVB-Pico 2 is a microcontroller evaluation board integrating our W5100S chip with the Raspberry Pi RP2350. It is designed to provide Ethernet connection for applications such as IoT devices and smart home system, etc., with a more simplified process in setting up internet connection. Before assembling our project, we need to set up our board to be used in CircuitPython. Go to the download page on CircuitPython, search for W5100S-Pico 2 and download the UF2 file. For the board, while holding the bootleg button, connect it with our PC using the USB to Type-C wire. Go to the board's drive and simply drag the UF2 file onto the drive. Your drive should look similar to this after completing UF2 installation. Next, let's connect the rocker module with the board. For my rocker module, we have a total of 5 pins. The 2 pins on the top will be connected to the 3v3 port providing voltage to the module and a ground port respectively. In this project, we only need the X pin as it tracks the vertical movement of the rocker module. Since the output is an analog signal, we can only connect this pin to the ADC ports, which are GP26 to 28 from our documentation. In this project, GP26 is used for the analog input and components are connected as follow. If you connected successfully, a bright light should turn on if there is a power LED on your rocker module. Let's now connect the traffic light module. Connect the negative terminal to ground of the board and the positive terminal to 3v3 port of the board. My configuration for this project is as follows. Next, connect the green, yellow, and red light port to the board. According to the documentation, we can only use pins ranging from GP0 to 15 as some of the pins are reserved for the SPI interface or analog signals. In my device, I have connected wires that reflect the color of the light for easier recognition and insert into GP11, 13, and 15 port for green, yellow, and red light respectively. Lastly, use the Ethernet cable to connect your device with your router. The hardware configuration is now completed. Let's move on to the next section on software implementation. Firstly, we need a compiler for coding our device. Go to CircuitPython webpage and use their online code editor to edit your code. Continue as follow. From the Connect tab, choose Connect with USB option. Connect your desired device to CircuitPython. Click on the Open tab and open Code.py. We will be building our codes here. Let's start by setting up the modules. Start by importing libraries for I/O configuration. We will need both analog I/O and digital I/O as we will be treating analog signals from the rocker module and transmitting digital signals to the traffic light module. Next, let's configure the pins on the board. For the rocker module, we first use analog in function to configure the pin GP26 as an analog input. For the traffic light module, use digital in out function to configure GP11, 13, and 15 to digital signals. We also need to initialize their direction as output. Lastly, put these LED variables to a list in the order of red, yellow, and green so that we can turn on or off the lights sequentially. Before coding the main program, we need a few more setups. Download the library zip file from Adafruit's website onto your local PC and unzip libraries you need into the lib folder of the board. In this project, you would need these 5 libraries. Now let's set up the interface on Adafruit. Create your account or sign in at the Adafruit's website. After logging in, click on the I/O tab on the top of the page, and you should arrive to the main page of Adafruit IO. Next, let's set up the feed. Go to the Feed tab and add a new feed. Label it as Power and create the feed. Notice there is a key value next to the name of the feed. This value will be used as the feed topic during data transmission. For our project, we would need 5 feeds including a power feed, a controller feed, and a feed each for the different colors on the microcontroller. You can change the name or key by clicking on the desired feed and go to Feed Info on the top right corner. Next, let's create the user interface. Go to the Dashboard tab and click on the default dashboard. Add your blocks by clicking on the settings icon. For the interface, we need to create a power toggle, a controller block, and 3 indicator blocks representing the 3 colors each. To set up the toggle block, bind the power feed to the block. Set the on value as 1 and the off value as 0 and create the toggle block. Next, to set up the indicator blocks, bind the 3 colors to the 3 blocks respectively. Rename the title and set the block on and off color with the feed's color and a color based on your preference. Set up the condition to equals 1 so that only the value 1 will turn on the indicator. Lastly, set up the controller block by simply attaching the controller feed to the block. You can press the buttons on the controller to see the values of each button press. The only 2 buttons we will use in the current project is the up and down button. The final dashboard should consist of these elements. Change the positions of the blocks to your likings. Lastly, you need to set up a file in order to be able to send or receive data from your dashboard. Click the link in the description about secrets.python and copy the code onto a text file. Before changing the JSON, save your file as secrets.python under the lib folder on your microcontroller. You can find your IO name and key on the top right corner of the page and simply copy the corresponding details from the website to your secrets.python. The other variables in the py file can be ignored in our project. Let's go back to our CircuitPython compiler and code our project. First, let's start by importing the libraries we need to the main program. You can copy the libraries in use from our GitHub page. Next, we would also need to import the secrets JSON stored in our secrets.py. You can use try and except keyword to import the library. This ensures our program contains our AIO information before running the main code. After that, let's set up the Ethernet on the board. The Pico board has reserved GP16 to 19 for SPI interface. Therefore, we can simply name the pin variables, assign the variables according to the microcontroller's documentation, and use our Wiznet 5K function from the Adafruit Wiznet 5K library to initialize an Ethernet interface using DHCP. To communicate with the designated server, we need to initialize the request session. In CircuitPython, the codes needed to form a request session has already been provided by functions inside different libraries of Adafruit CircuitPython. By using these functions from imported libraries, we can now transmit or receive data from the World Wide Web. Next, let's set up our network communication method with our Adafruit page. Currently, most platforms supports both HTTPS and MQTT method for communication. MQTT will be used and explained in our project. We first set up our board as a MQTT client. By inputting the corresponding parameters on the MQTT.MQTT function, the board is now a MQTT client ready to connect to the server. Next, we need to define what our program will do after establishing the MQTT connection. Define one function when we connect to the server, one when we disconnect to the server, and one when any feed subscribed has an update. In the connected function, we would like to subscribe to the power feed and the controller feed, as our user interface can change the power or change the lights when we press the controller. According to Adafruit IO's MQTT API page, we need to bind our username with the feed key before interacting with Adafruit IO. Therefore, we need to define the power feed and controller feed as follows. Let's also define a feed list for the lights in the order of red, yellow, and green feed. Finally, set a list for power and controller feed and run a for loop to subscribe to the feeds inside the connected function. As for the disconnect function, we can simply write a print statement to show that we as the MQTT client has disconnected from Adafruit IO. Lastly, in the message function, we want each update in the subscribed feed on the user interface to update the state of our board. As we subscribe to the power and controller feed in Adafruit IO page, updates in these feeds on the UI would either turn off our machine or change the state of the lights. Let's set up the function for turning off the power of the board. We first initialize a power variable as true to indicate our machine has started running. This will keep the main program to loop continuously until we turn off the machine. Next, we need to check whether the user toggled the power block or not. If the power block is toggled, we can then change the power variable by reading the message and using the global keyword to change its value. As for changes in the controller feed, we first need to identify which button has been pressed. During the setup section, we notice that pressing up gives a value of 5, while pressing down gives a value of 13. Firstly, we need to identify if we reached the maximum or minimum light that could be turned on. In our algorithm, I first defined a variable that tracks the current position of the light that is turned on. By making use of the previously defined list on the LED lights, we can access the sequence of light. That means that as the pointer goes to index 0, it refers to the red light, 1 for yellow, and 2 for green. Going back to the message function, if the pointer is equal to 2, it means that all lights are turned on, and if the pointer is equal to -1, it means all lights are turned off. After treating the upper and lower bound cases, we can build our algorithm for turning on or off the lights. To turn on the light, we would need to increase the tracking pointer first, and then turn on the LED of the new position. We can then publish the value changed to Adafruit IO using MQTT.publish function. And to turn off the light, we would need to turn off the LED on the current pointer first, and then decrease the pointer. Unlike the previous example, we publish the value of the LED that has been turned off before the pointer changes. Lastly, add the global keyword to LED set and the pointer for any adjustment inside the message function. The message function of the MQTT client has been completed. Our next task is to write the main program. We should start by connecting our MQTT client to the server. Use the mqtt.connect function to connect to Adafruit IO, and it will run the connected function we previously defined. We also need to publish to the power feed since we have turned on the machine. For the main program, we can use a while loop to continuously loop the function where the rocker module would change the state of the LEDs until the power has been turned off. Use the loop function of MQTT client to maintain connection between your board and Adafruit IO. We should also set a variable to store the current value of the rocker module's vertical movement. If the value reaches an upper threshold of 60,000 or a lower threshold of 3,000, we would turn the lights on or off respectively based on the light response algorithm defined previously. At the end of the while loop, a time.sleep function is used to reduce the load to the microcontroller by the while loop. Lastly, when the power is off, we need to reset everything on the feed to its default state and disconnect from the server by using the disconnect function. This concludes the codes for our project. Thanks for watching. I hope that by this video, you understand more on how to use our W5100S-EVB-Pico 2 with CircuitPython and start your creation journey on developing your own IoT project. Links about our board and this project will be provided in the description below. Play around with the device if you have coded with us, or you could find the codes by going to the GitHub page under the description to try it out. Comment down below if you have any questions. New videos will be coming out soon, so be sure to like and subscribe to our channel. See you soon!